All right. Thank you, Ryan. My name is Mike Smid, Executive Vice President for TEC. Today, we're going to talk about high efficiency cooling towers, approximately 40% higher, more efficient than the traditional cooling towers out there. But one of the things we're going to look at today is we're going to compare it versus other systems out there also. So oftentimes when we do cooling tower comparisons, you're dealing with a cooling tower manufacturer, and that person is really invested in trying to sell you a cooling tower. From our side of it, we look at complete system. And if the water-cooled cooling tower makes sense, it makes sense. If the air-cooled system, air-cooled chillers makes sense, it makes sense. So we're going to walk through a little of that as we go through. But as a product itself, we've been handling this product now for 7+ years. One of the best products we've ever taken from a reliability standpoint. Just an absolutely fantastic product and great company that we represent in Tower. All right, so we're going to do an overview. We're going to look at the evolution of cooling towers. Then we're going to look at common operational challenges and best practices. We're going to look at what is the cost of water in Chicago. That's a big one right there that we're focused on. We're going to do some sample energy analysis on the cooling tower system from the energy side of it only. And then we're going to do a complete system. We do air versus water cooled in the city of Chicago, where we look at energy and we look at water. Our objective is today. If you have any questions, Ryan will alert me as we go through if there are any questions, and we'll answer them accordingly. Okay. So when we look at from a technological innovation standpoint, one of the things we look at a tower to tower on the side of a building, it's a galvanized piece of material. Everybody's towers look the same. It's a fan with a gearbox on top. Thing that has changed over the years. Maybe it's different material, steel, fiberglass, and then VFDs was a big energy innovation. And then maybe you do davit arms and maybe a little bit of different nozzle technology. But Tower Tech's a little different. So I'm going to kind of walk you through a couple of slides and show you what's the difference between a Tower Tech tower and everybody else in the market. This is a before picture, after picture. Before.
Hey, Mike?
Yes.
Can you hear me, Mike?
I can.
All right, your audio is cutting in and out pretty bad. I don't know what kind of audio connection you're using or microphone.
Yeah, let me try. Maybe I'll call in with my phone here.
All right, let's give Mike 30 seconds, guys, and see if the phone connection's
I'm using the computer, but
yeah, make sure you mute your computer when you're calling from the phone. It sounds good right now.
Okay. You want me to try it one more time on the computer? I was working from it on the side. So let me try it. Let me try it again here.
Okay. I'll let you know if it's
no. Where was I breaking up? Did you break up through that?
You're good right there. Start from there.
All right. So let's going to talk about the and if I'm breaking up again, I'll go to my phone. But I switched from a different system. So we're going to talk about the evolution of cooling towers, the common operational challenges and best practices, and really what is the true cost of water in Chicago. That's a big point we need to focus on. Sample energy analysis on a cooling tower project. And then we're going to look at a project of an 800-ton chiller plant where we're going to analyze a air versus a water-cooled system in the city of Chicago. From a technological standpoint, cooling towers really haven't changed in a long time, right? So it's a galvanized box with a fan on top, with the inlets on the sides. Maybe there's some change in the fill. Maybe sometimes once in a while you see a plastic tower out there. VFDs was the big innovation, 10+ years ago. And then maybe you go to a davit arm or different nozzle. The Tower Tech tower is purely, it's absolutely unique. So we're going to go through a couple of before and after photos of actual jobs. Again, another before and after photo of a job. And then a current system where they have multiple towers lined up on a system. So this is a snapshot of like the inside of a TowerTech cooling tower. I'm going to first of all work the water side of it first. So the water will go into the inlet on the upper and middle part of the tower, and it'll flow through the variable flow nozzles, which are shown in blue here. Okay, those variable flow nozzles vary the flow down to a third of the design flow. It's really only nozzle that's a variable flow nozzle. Then the water goes through the fill, and then it goes into our water collection system, which then flows into, so here's our water collection system, and then it flows into the high velocity basin. Okay, so water in this system is always moving very quick, is moving at a rate of 5 to 7 feet per second. So it's very tough for anything to, stay into the system and be stagnant water. Okay, I'm going to walk back up a little bit. Now let's walk through the air side of it. Air comes in through the fans on the bottom. That water collection system has a damper. So as the fan is running, the air actually flows through that water collection system, through the fill, up to the top of the TowerTech tower. And what's different, obviously, from a TowerTech tower is our fans are on the bottom, and you see it's like a fan array on the bottom. So at one point, so we have a bunch of fans on the bottom, we're blowing air up, and we're going up through the top. The other thing that's unique is you have no exposed water to sunlight on this cooling tower. So if I don't have water and sunlight, that means we don't have algae. If you look at a traditional cooling tower, when you walk up to it on the roof, first of all, you feel the droplets on the side of you as you're walking next to it. And the other thing is you see algae all throughout that, the fill of the cooling tower on a traditional tower system. So let's talk about some of the traditional issues. So when we look at airborne dirt on a cooling tower, the cooling tower is basically an air scrubber. Okay, so we have a fan that's moving air across fill, and it's grabbing the dirt that's all around that cooling tower and sucking it in, and we're discharging it out. What it does is at that point we need water treatment to effectively treat that dirt. But what happens eventually is that dirt then ends up on the condenser tubes in the chiller. And if we lose 1 degree of approach on that chiller, it decreases the chiller efficiency by 1.5% loss. Now, that may not seem like a lot, but we're talking about a big horsepower motor is that chiller plant. So 1.5% loss is a big deal. Obviously, with the airborne dirt, we have increased maintenance and we have less thermal performance. From a conventional standpoint, what do? More frequent cleaning, basin sweeper systems, and larger filtration. The TowerTech approach, what we're doing is we are typically, most of the time, we're on a 6-foot line. So that tower sits up 6 foot high. Air comes in through the bottom, so the dirt is less. It takes a tougher pathway to get into the system versus a traditional system itself. So we typically have less dirt, debris. Our condenser tubes need less cleaning, so therefore the chiller plant operates more efficiently. And in essence, we can have higher cycles of concentration, which is a big savings in water. From a water side of it, we're talking about a typical 1,000-ton chiller plant, an average load of 6 months. It uses about 10 million gallons of water per year. So the TowerTech will save approximately 10% water savings, which is 1 million gallons of water per year. What's going to happen next as what's starting to get adopted into California is using the treated sewer water effluent for toilets and cooling towers. The problem with that is the treated sewage water is rich in potassium, and on a conventional tower system, which is galvanized, and then sometimes a stainless steel basin, it could eat the material. And everything on a traditional conventional cooling tower is also, that motor is in the airstream. So that water is basically hitting your gears and your motors before it dissipates, versus a TowerTech tower, the fans are on the bottom, so that water is not affecting the fan system on that cooling tower. So from a water conservation standpoint, we mentioned before that the air comes in through the bottom and discharges at the top. You'll notice on a traditional tower, it goes through a high velocity point where the fan is on the top of the cooling tower. It's a higher velocity than the velocity that we're discharging off the top of the cooling tower. It is a lot larger surface. Because of that, we have 0.0004 drift emissions on ours versus the traditional tower of 0.001 or 0.002 drift emissions. So in the other part is we have a heavy pull treated fiberglass cooling tower. So that means that tower can withstand that treated sewage water effluent. It's not a galvanized material, and we have stainless steel bolts. Okay, so that's the big thing on water conservation. But this is the bigger story right now. Okay, so this is back when we first started working on with Tower Tech. This was an article I pulled up in 2012 where Chicago water rate hikes ripple. So at that point, Mayor Rahm Emanuel announced plans to nearly double the rate of Chicago charges to its neighbor in the suburbs. Okay, let's see what has happened since this article. So 2012, the cost of water was like $3 per 1,000 gallons. It was a lot less than what it is now. 2016, it went from $7.62 per 1,000 gallons, $8.21, $8.90, $9.63, and then this year the water cost went up to $10.13 per 1,000 gallons of water. We live next to one of the largest freshwater bodies of water. We are top 10 in water costs in the country. So this really needs to be taken, we need to look at this when we're doing our analysis on the cooling tower itself. A material and life expectancy, we got chemical treatment and hard water, and typically manufacturers, when they're designing things now, as much as we hate to say it, people are always trying to figure out ways to make things thinner and cheaper. Okay, so traditional tower system uses a galvanized tower and a stainless steel basin. Those are two dissimilar metals, which could cause galvanic corrosion. 5-year structure warranty, which is parts only. And they have a per ASHRAE 15 to 20 year life expectancy. 8 to 10 in some cases, depends on the water quality. Tower Tech approach, it's a pole-treated fiberglass reinforced polymer cooling tower. 15-year structure parts and labor warranty on the tower structure itself, and a 35-year life expectancy. So when our tower is installed, and typically it's installed with a chiller. On retrofits, it's not. But on a new application, you expect that chiller plant to last, 30 plus years if you can get out of it. I know ASHRAE says 22, but you'd love it to last 35 years. So our cooling tower and our chiller are meant for that same exact lifespan versus installing a traditional tower and then doing a major retrofit on that cooling tower, maybe 15 years and 20 years into the life of the tower. So we're eliminating that piece of it. Now, you may have to replace the fill in that time period, obviously, but not the structure side of the cooling tower. So we're going to talk about Legionella from a cooling tower standpoint. So typically grows in a cooling tower basin with stagnant water, transmits through the drift emissions. So as I mentioned earlier, when you walk around a traditional tower, when you go up on the roof or on the side of a building, you'll notice the droplets of water when that machine is operating in the summertime. Okay? And at that point, sometimes the drift goes into an outside air duct, or it's inhaled somehow at the job site, and that's a lot of the cases sometimes when we see Legionella. Conventional approach is thorough cleaning, at least quarterly, basin sweeper systems, a filtration system, and then a low drift rate for that conventional tower system. Tower Tech approach, obviously annual cleaning. We're using a high velocity basin on our water collection. That water is moving 5 to 7 seconds, which it's very tough for Legionella to grow in a tower that, first of all, has no exposed sunlight to it, so no algae, and also where that water is always moving. Okay, and then obviously a filtration system, but our drift rate is far less. There was one particular job that we sold where they were putting a tower in a parking lot, and it was right by cars, and they didn't want to have the drift going on cars. And the reason why the Tower Tech was sold was because of its drift rate versus the traditional tower system. That was really the only reason, of obviously the energy and the water savings and everything else that goes along with it too. Why do we have to be concerned about Legionella? Because ASHRAE standard 188P says we have to. This is more of the building operator standpoint. When there's a standard, there could be some issues if you don't adhere to that standard when we talk about water. From a Legionella standpoint, we have obviously cases popping up all over here every year. I think 4 or 5 years ago, New York had an issue where they were doing mandatory, like quarterly maintenance requirements on the cooling tower because it was an outbreak. Multiple direct drive fan advantage. Okay, this is a big one. So typically owners, they want redundancy in their system. On a traditional system, you have a cooling tower that's attached to a chiller. If that cooling tower fan fails, typically that chiller cannot operate. If that chiller cannot operate and that system goes down, then I better have some sort of redundancy if it's a critical chiller. So a common approach for the conventional system is just putting in another tower. So if that one fails, then we go to another one. However, that's expensive from a piping standpoint, install standpoint, material standpoint, control standpoint, everything standpoint. In the tower tech side of it, we have multiple direct drive fans. So on a traditional 1,000-ton chiller plant, say 3,000 GPM, we can offer a 12-fan system. That's the largest fan system. And if one fan fails, we can assure that we can operate that load with 11 fans on that system. This saves the owner an extra cooling tower footprint, controls associated with installing an additional tower. So this is a great approach when we talk about the redundancy of the tower tech system. It's like a fan wall in the air side of it, which everybody likes fan walls on the fan side of it on an air system. This is a cooling tower with fan wall. So I want to talk a little bit about the tower tech design and water system. So you'll see here, this is a picture of the plan view with 100% GPM for tower tech. You'll notice that all the water in the fill is covered. This is 100% GPM and 100%. A conventional cooling tower system, the Weir system, we have 100% flow. All the fill is full, just like tower tech. So very similar in that sense. Where we're getting our energy savings is right here. So at part flow, let's say we're running at 50% flow. In this case, what's happening is we are covering all of the fill with half the flow. So the efficiency on a cooling tower is basically, it's pretty simple. You need surface area to cover. If you can cover that fill with as much surface area as possible, at that point, I could reduce the fan speeds of the direct drive fans. Then we save significant energy savings. On a traditional system, you look on the right-hand photo.
Mike,
on the Weir system, yes?
your sound's degrading much worse again. Like the past 3 or 4 minutes has been degrading pretty bad to being unhearable, if that's a word.
Okay. I'm going to switch over to the phone, Ryan.
Okay. Yeah, it was good for a little bit, and then we lost it again.
Where did you leave off? Multiple direct drive fans?
That's fine. I don't know exactly where it started interrupting long term.
All right, let me
call in on my phone. And then it was an issue. All right, we'll give you a few minutes to call in here, or a few seconds. In the meantime, everyone can listen to my musical stylings as I tap my pencils on the table. That's all I got. I don't have anything better than that. Hopefully Mike's cell phone microphone is awesome. Worst case scenario, I'll talk about cooling towers. I'm pretty knowledgeable. We could probably go at least 6-7 minutes before I run out of information on that topic.
Ryan, can you hear me?
Yes, we can hear you, Mike. Let's give it a shot.
All right. Sorry about that, guys. I was trying to use the computer. Hopefully the message is getting across. So where should I start off? The multiple direct drive fan advantage, yeah. Ryan?
That would be good. Yeah, you were good for like 10, 12 minutes straight, and it was fine. And then it dropped out a little bit again, and then it started more and more. So I think if you start right there, you're good. Sorry about that.
Okay, so let's talk about the multiple direct drive fan advantage with just with TowerTech. So the problem is the owner wants 100% redundancy. The common approach with multiple towers is, in order to meet that 100% redundancy, if that fan goes down, we need another cooling tower active. So that means you're buying another cooling tower in order to meet your N+1 requirement. The TowerTech approach is we're going to use the multiple fans to our advantage in the system. So let's look at an example where we have a 1,000-ton cooling tower, 3,000 GPM. We're going to put 12 fans in that. Now, that's the largest fan system we offer on the cooling tower system. So if one fan fails in the system, we're able to operate at 100% capacity with 11 fans in the system. Okay, so this will allow the end user to save in footprint, install cost, controls, everything on a system by going to this. Once we hit that point, this system is obviously paid back versus a traditional system. Okay, so we're going to look at the TowerTech design. Here's a planned view of fill with 100% GPM for a TowerTech system, and you'll notice that the fill is all filled. This is 100% flow. When we look at a traditional system, conventional tower system with the weirs, what they have is, again, the fill is all filled, 100% full GPM, design day, conventional cooling tower. So in this case, we're very similar to an efficiency standpoint. However, when we drop this down to 50% flow, this is where we have our significant advantage. So at 50% flow, we're able to cover the full fill of that cooling tower and not have dry air disease like traditionally happens in a cooling tower. And so we have a high liquid to gas ratio on the fill, which allows us to then run our fans at reduced speed with the VFD, which saves significant energy at part load. And most of our chiller plants are operating at part load. The conventional system on the right, what's happening is on the weir system, when that gets to 50% flow, we're no longer using that side of the fill. So at that point, what's happening is we have less, so it's the same basically liquid to gas ratio. So they're not gaining much efficiency at part load when they run reduced flow through their system. So we're going to look at the overall system efficiency. So the total installed horsepower, we're going to look at minimum fan motor frequency allowed by VFD, the pump head, we're going to analyze that, and a variable flow turn down capability while efficiently covering all the fill media within the cell. So on a traditional tower system, when they're running at 100% flow, you have a very circular nozzle pattern that overlaps. When they drop down to flow less than 15% of the design flow, or less than 85%, full 85% of it, they get in a pattern like here, and then they get dry air disease. So they don't recommend dropping and running their system with less flow. The TowerTech system, you can see a snapshot of a variable flow nozzle in operation. So what happens is the water goes through the nozzle, its pressure then basically allows it to spray in a square pattern and cover the complete fill of that cooling tower. Okay, this is a snapshot of the tower with the top fill off. Okay, this is just showing as a site view of how the nozzle works and operates. So this is an actual design. This is an actual job in Chicago that was installed, probably 5-6 years ago. We'll show the analysis on it. This is a 2,700 ton system, 8,100 GPM, 95 entering leaving water, 85 leaving water of the tower, 78 wet bulb. We have 3 900 ton chillers, and the operation is 7 months a year. And we're assuming 10% operation at 2,700 tons, 45 at 1,800 tons, and 45 at 900 tons. So we're going to do a comparison. The most popular fixed orifice cooling tower, 3 900 ton cells. They have 60 horsepower per cell with a total horsepower of 180. Their minimum frequency, because they have a gearbox, is 25 hertz, and they have 19 feet of head on that cooling tower. Versus the TowerTech solution, which is 3 900 ton cells. We're running 60 horsepower per cell with 180 total horsepower, and then a minimum VFD frequency of 6 hertz with 13 feet of head. Now, on paper, when we looked at this traditionally, we would just look at the full total horsepower of a fan, of a cooling tower, and say, They're very similar because they're both at 180 horsepower total horsepower on a cooling tower system. However, we're going to do the full analysis on it. And we're going to use pump head equals Q times feet times the constant in the pump efficiency. So at 2,700 tons, this is design day load. The fan horsepower is 180. The pump horsepower is 46. On the traditional system, it's 226 horsepower. On our TowerTech system, our fan horsepower is 180, similar to conventional. But because we operate with less head, we're at 31 horsepower. So we have a total horsepower advantage on design day of 7. That's not very significant, but we have a 7% advantage on design day. Part load is where we see the significant advantage. Traditionally, on a tower system, as you turn a chiller off, you turn a tower cell off because we have less flow and it can't handle reduced flow in the system. So in this case, their fan horsepower is 120. The pump horsepower is 31 for a total horsepower of 151. In the TowerTech solution, because we can operate with variable flow through the tower system, we're going to operate 2 chiller flow through 3 tower cell. So we're going to have a ton of surface area on the fill side of it, and then we're able to reduce the horsepower of the fan system, and we also are operating with less pump head. So we have a total horsepower savings of 60. We have a total horsepower of 69. So we have a 54% advantage on a multiple chiller plant in this case. I had 1,800 tons in this one. At 900 tons, the traditional tower system, again, we turn off a chiller, we turn off a cell, and they're operating at 76 horsepower. There's a certain point where we can't operate one chiller through 3 towers. So we're going to turn off a cell, and at that point we have 1 chiller operating through 2 cells, and in this case we're operating with a total horsepower of 31, and this is a 59% energy savings at that point in the chiller plant. So when we do the full analysis overall, we had a 48% energy savings over a traditional tower system. And additionally, because we're selling the chillers and the cooling tower, we're using the head pressure reference signal from the chiller itself to operate with cold condenser water. When we did this analysis, what we were able to do was we were able to save an additional $8,400 a year on operating the chiller system with a tower. So this is a unique piece what TEC has the ability to do is we know how a chiller operates. We know how a cooling tower operates. We know how the whole entire system operates. And that's unique into the Chicago market that no one typically has. So we have that knowledge of how we can operate that system as a whole the most efficient way. From a maintenance and reliability comparison, strainers, obviously monthly on both systems, nozzles, monthly for the conventional system. Our nozzles are, they call them like a non-clogging nozzle, but we recommend you inspect them semi-annually. Cold water basin, conventionally quarterly, we do it annually. Air inlet louvers or water collecting systems, they do it monthly, we do it annually. Fill media, semi-annually, we say annually. And then clean fan motor exterior, they're quarterly. Now they have a gear system, okay? We have direct drive fans, so we're doing it annually. They have this whole entire other line of things. Lubricate fan shaft bearings, check oil, change oil. Those are all part of a traditional tower system. And that's not free to an owner. That actually costs money. So when we look at this system, we're able to save maintenance side of it. But because of the redundancy of the multiple fans, a conventional tower in that last example we gave you, if one tower failed, we only had 67% capacity available. Okay, on the TowerTech solution that we just showed you, if one fan failed, we had 99% available performance in that system. So this is analysis we're going to do. We're going to look at a TowerTech cooling tower, and we're going to match it up with a Carrier 23 XRV system, and we're going to look at an 800-ton chiller plant with one TowerTech tower. Okay, and we're going to use 2 Carrier 400-ton 23 XRV chillers. So we like the design that we like to do in this market is when it can be done with a 2 chiller plant is we like to operate 2 chillers with a single tower. Most of the time you're operating those chillers is 1 chiller is operating at a time. So therefore I could take advantage of the energy savings and the reduced fan speed on the TowerTech tower itself. So this is kind of a snapshot of the system. We're going to look at 2 options. on this job. We're going to look at one, a water-cooled option, and we're going to look at two, an air-cooled option. And this is where I'm going to say, you know, like, listen, we feel like we have really learned a lot about this whole entire cooling tower business over the last 8 years we've had this product. And we're going to steer the contractor and the owner in the right direction based on overall operating costs. I don't have any, I really don't care if they want to go to the water-cooled system or if they want to go to an air-cooled system. Either way, we have solutions for both. Okay, so that's what we're going to look at right now is we're going to look at two different solutions. So the option one is two 400-ton Carrier 23X RVs and an 800-ton cooling tower. And in this case, this cooling tower is operated, these 400-ton chillers, you can see it's an ultra high efficiency chiller running at 0.55 kW per ton full load at 0.33 IPLV. The cooling tower itself is 800-ton cooling tower, 2400 GPM, operating at 37.3 brake horsepower. So our option two system is going to be two 400-ton ultra high efficient Carrier 30XV chillers. Now this has got a part load value of 20.11 BTU. So when we look at that and we put it into a kW per ton, it's operating at like 0.59 kW per ton and an air-cooled system. So our air-cooled systems have gotten so efficient, and with the cost of water, you sometimes find this is a more economical install and a better solution for an owner. So we're going to look at two different systems on it, and this is how we're going to make the analysis.
Hey, Mike, can we ask a couple of questions?
Go for it.
All right. Lawrence asks, is there a shipping weight difference and is there an operating weight difference?
Job to job, but not. We have not seen a significant difference in operating weight or shipping weight on these systems. And actually, one of the things I didn't discuss on this is the way this thing ships, and this is what's unique into the installation part. And I didn't even hit this in the presentation, and I'll show it in a picture here when I show the cooling here. If you look on this picture here in the cooling tower, those legs, we have entered into a new design where now when it shifts, those legs now fold up on the tower. So when the unit comes off a truck, it actually pulls up, you fold down the legs and you put it in place. If anybody has installed a traditional tower system where you have the basin and then you have the tower you have to stack on top, you have to make it sure it's completely aligned and all the gaskets and everything is in place. So from an install standpoint, but as a whole, weights, no, it's very similar to a traditional system.
One more question, Mike. Lawrence also asks if it's CTI certified.
Yes.
All right, that was easy. All right, we're all caught up on questions.
Yes, it is.
Anybody else has questions?
Okay, so
type them in and I'll read them off for Mike. Thanks, guys.
Okay, so we have two 400-ton 30XVs. So when we do the operational analysis on this and we look at the energy cost of operating option one versus option two, when we look at this, and this is oftentimes when we stop the analysis, and from an end user standpoint, they're like, man, that Carrier 23X RV / Tower Tech system is an operating cost of $33,000 a year on an 800-ton chiller plant versus an air-cooled system of $53,000 per year. It's a savings of $19,000. I mean, that is significant. There's no way water costs that much. However, we need to analyze that because we live in Chicago and our water cost is $10.13 per 1,000 gallons. When we take that into account, the water cost for this 800-ton chiller plant is $68,000 a year. Okay, so when we look at that with water, sewer, chemical, we're looking at a $68,000 water cost per year. And in this case, and this is where I always try to make sure everybody's analyzing the full system. Okay, I'm not saying go water cooled, go air cooled. Sometimes you're forced to go water cooled because that's what you have in the building and you're doing a replacement and this is what I want. And I'm going to show you the examples after this of how we compare versus the competitors. And in that case, but if we're doing a new installation in a new building, air cooled makes a lot of sense, 800 tons and below. When we start getting to that larger tonnage, that's where water cooled really starts taking effect and we get the advantages of the water cooled system above. But from my advantage, what I've seen out here is I've seen 800 tons below, air cooled makes a lot of sense because of the cost of water. So from a summary standpoint, option 1 versus 2, if we just looked at energy cost alone, the water-cooled plant would have won. However, when we factor in water cost, obviously the ultra high efficiency air-cooled, because air-cooled machines have gotten awful efficient. In this case, the air-cooled machine wins, okay? When we analyze the complete system, you have to analyze the complete system. Let's look at first cost, install cost, and operating costs. Now, operating costs, that includes the water and the electricity and the maintenance, okay? And at the end of the day, talk to your TEC TM. We all know this. If you need my help, I'll help out anytime anybody needs it in doing these analysis at the job site or on a particular job. I've done a ton of these projects myself where we've done the analysis to 10 users. Now I'm going to analyze the Tower Tech solution. Let's say we have a tower that has to be replaced. It is a water-cooled system. It's staying water-cooled. We want water-cooled. In this case, we have an 800-ton system comparing it against one of our competitors. So we're using an electrical rate of 8 cents per kilowatt hour, a sewer cost of $5.13, water cost, we have a total combined cost of $10.13 per 1,000 gallons, and then we have a chemical usage cost. When we do this analysis at 800 tons, we are going to save that end user about 321 gallons per year on the water side of it, in this case. And then from a fan consumption kW, we're saving significant energy on the fan system because we could operate at part load. We could operate at lower horsepower on the fan system. So 95,000 versus 140,000. And then when we do the full analysis on an annual operating cost, it's about $16,000 a year energy savings and water savings versus a traditional cooling tower system. Tower Tech is a premium tower. We will be more expensive than every tower out there, sometimes by a factor of 50%. But when you factor in all the other things, okay, I have the energy saving, water savings, I have the longevity of the equipment. If you are an owner operator of the building, you're going to save in chemical treatment costs. And I know that in year 10 and 15, I'm not going to have to do a complete retrofit on that cooling tower system.
Hey, Mike.
Yes.
In regards to the chemicals, Pete asks, what is your breakout for chemicals for estimating purposes?
That was they're using $3 per 1,000 gallons for chemical usage. That's just a factor they're using in the program. So with the Tower Tech, and that in order to do that, then I have to look at the cycles of concentration. So that's a factor we're using in the analysis when we're coming up the dollars. But you'll see it on the next slide where you see a dollars factored into the chemical usage. So we got to look at an 1,100 ton plant. This is a recent project we looked at where the end user liked the idea of going with the Tower Tech solution. This is an 1,100 ton chiller plant. Again, same energy. Actually, I used slightly less cost for water. In this one, in this particular case, I rounded it at 10 in this example. But in this one, we were saving the end user just under 1.4 gallons a year of water, 1.4 million gallons a year of water, okay? And then from a fan system, we were saving some on the fan, but you'll notice I'm not playing favorites here. In this case, it took a little more to pump the water through our machine, so we had to take a 5,000 kilowatt hour hit on the pump side of this tower. However, when we look at the overall savings of the job, it was about $20,000 a year in operating cost savings between fan, electrical, water, sewer, and chemical. And in this case, it was somewhere of a payback. At most cases, we'll find is a payback of 5 to 3 years from a payback side of it. And if it operates year round, it's much more. It's less than that. So, from a summary standpoint, we have multiple direct drive fans. So we give the owner built-in redundancy. This is a key. There's no emergency phone calls, right? So when on a traditional tower system, if that fan fails, or something goes wrong with that fan system on a traditional tower, that's an emergency call. That's a crane, labor that has to fix it. On ours, we have a direct drive fan that's underneath. I have one guy that can actually, if he has the proper material, he can actually do a replacement of that motor system on his own. As we have the lockout, tagout, and the motor protection panel, we can operate all the other fans in the system and it's not an emergency phone call, which means I'm not paying overtime from a service side of it. Variable flow nozzles allow the tower tech machine to operate more efficiently. As we said, at part load, we're running one chiller. We're running half the flow through the full fill. We're able to reduce the fan speed. We can operate down to 6 hertz on a direct drive fan. So we can operate very efficiently at that point. Again, we have less dirt and debris in our system, which allows the tower to operate with higher cycles of concentration, which allows us to use less water, which in Chicago, as we mentioned before, it's a very big deal, okay? And then the pultruded fiberglass design will last an owner 35 years. So those are all big things. And the last piece, do a complete system analysis, and any one of your folks from TEC will help you. And if they can't, I will help them do a complete analysis on the water-cooled system itself. So with that, Ryan, I think I flew through that pretty good in 40 minutes. Wow. So I will take questions.
Faster than me in this company.
Hopefully everybody understood what I said and I didn't fly too fast. So
yeah, we're good. We had a little microphone issue early on, but we were good after that when you switched to the phone. If anybody has more questions for Mike, please type them in. We'll give it a minute or two and see if any more come in. I think I've read off the ones that we had, though. Even if you have other questions about chiller applications, I'm sure Mike would take those too, even if it's not exactly.
And we're gonna do a chiller plant analysis. It's a Tuesday, right?
Correct.
So we're gonna do
today's webinar.
We're gonna do a ultra high efficient chiller plant webinar. This one will actually be for PDH credits, but we'll do that on Tuesday, and we'll talk more on the chiller side of it versus the cooling tower side of it.
And for those that are looking for those webinars, we e-blast them out, and you're probably on those lists. Also, if you go to tecmungo.com and click on training, there's classroom training and webinar training on there. Click on the webinar one and you'll see all those upcoming webinars, as well as recorded ones like the one we're doing now, as well as our video channel. Lawrence asks, how can you eliminate the sweeper system?
So the sweeper system, we don't have a sweeper system because we don't have a basin, a high volume basin in our unit. We have a high velocity water basin, which water is always flowing. The main piece on the sweeper system is to keep water from stagnating on the system, which I think is required in a hospital. So we are using the high velocity basins on the cooling tower for water movement. So that's how we're doing this.
The way I think of it is if you have like a retention pond by your house, they may put an aerator in there, a fountain in there to keep the water moving. But if you have a creek going by your house, the water's already moving, so no need for an aerator.
Correct. I agree 100%.
Anybody else have any other questions we can interrogate Mike with right now? All right, well, with that, we are going to wrap it up. If you do have other questions, just hit Mike or hit me or hit your TM, and we'll get you guys the answers you need for the applications you guys are working on. Thank you very much for your time.
Thank you. Take care.